There, some clicky pen ASMR, I suppose. Anyways. So, in today's problem, we have a 0.3 kilogram cart moving at 2 meters per second to the right as it collides with a 0.1 kilogram cart, which is initially moving 3 meters per second to the left. After the collision, it is said that the 0.1 kilogram cart moves to the right with a speed of 0.1 meters per second, and we assume that friction is negligible in this problem. So before I start, I always like to draw a just quick, very basic sketch. So here we have the 0.3 kilogram cart, and it's moving to the right at 2 meters per second. Now, here I'll use a different color for this. We have a different cart. This one's lighter with less mass. It has 0.1 kilograms of mass, and it's moving faster with 3 meters per second, sorry. Now, the first question is asking us to calculate the magnitude and direction of the velocity of the 0.3 kilogram cart after the collision. So this is just a very basic conservation of momentum problem, so let's set up the equation first. You'll have m1 v1, that's of this cart, we'll call this cart 1, and we'll call this cart 2, plus m2 v2, now these are the initial momentum, and that's equal to m1 prime v1 prime plus m2 prime v2 prime. Now we just plug in the knowns and solve for the unknowns. So for m1 v1, we know it starts out with 0.3 kilograms of mass and traveling at 2 meters per second. M2 we know is 0.1 kilograms of mass rather, and is traveling -3 meters per second. Now the reason we do negative is because in the equation of P equals mv, these are both vectored values, so the direction does matter in this case, so negative is the left direction. Now this is equal to the same mass of the cart, obviously it hasn't changed mass, times v1 prime. Now that's what we don't know. Now for the second cart, we know that it has the same mass, again 0.1 kilograms, and is now going 1.2 meters per second to the right, so that's a positive value. After some manipulation, you plug it all in, you end up solving for v1 prime, which will equal, just plug into the calculator, 0.3 times 2 plus 0.1 times -3 minus 0.1 times 1.2, all divided by 0.3, and the answer comes out to be, I don't know if you can see that, 0.6. So v1 v1 prime rather, sorry, v1 prime equals 0.6 meters per second. And that's all it takes for part A. Now on part B, it's a more conceptual question. It just asks, is this an elastic collision, and justify our answers. So for this, it's important to go back to what we know about elastic collisions. I'll do this on the side. Elastic collisions demonstrate two things. One is that momentum is conserved, and this is the case for almost all collisions. Actually, it's the case for all collisions. Momentum will always be conserved. Let's see if I can spell. But in an elastic collision, what's also important is that kinetic energy is conserved as well. So let's take a look at our problem here with the two cubes. So knowing that kinetic energy is equal to 1/2 mv squared, let's see this. So the best way to see if kinetic energy is conserved is just take Ke initial, the initial kinetic energy, which we have 1/2 m1 v1 squared plus 1/2 m2 v2 squared, and then Ke final, which is 1/2, the m's should stay the same, so m1 v1 naught squared plus 1/2, I said not, I meant to say prime, 1/2 m1 v1 prime squared plus 1/2 m2 v2 prime squared. Plugging in known values again, you end up getting 1/2 times 0.3 times 2 squared plus 1/2 times 0.1 is -3 squared. The negative actually is superfluous because energy is not a vectored value, but rather just a net magnitude. And then for the final, it's again 0.3 kilograms. It's now traveling at 0.6, as we solve right above here. And then again, M2 hasn't changed, and V2 is still 1.2 squared. Now you end up getting, I'll save you the time, I did the calculations earlier, 1.05 joules and 0.126 joules. Now because these two are not equal, nope, it is not an elastic collision because kinetic energy was not conserved. And that's our answer for that. Now, part C asks that once the 0.3 kilogram cart was removed, the 0.1 kilogram cart, the second cart, that's a red one, continues to move to the right and then collides to compress an ideal spring whose right end is attached to a fixed wall. So if we are still imagining the same 0.1 kilogram mass, but is now going in the right direction at 1.2 meters per second, and then it hits a wall, this will be our wall, and attached to the wall is a spring, and that's my perfect rendering of a spring. Anyways, so what happens when it reaches its maximum compression? Now, what we know about potential and kinetic energy is that energy is going to be conserved. So this is a basic conservation of energy problem. So let's write out the full equation, the work, plus the initial kinetic energy, plus the initial potential energy, is equal to the final kinetic energy, plus the final potential energy, and any energy that might be dissipated. Now, immediately already we can cancel some things out. There is no work involved right here. There was no outside work being applied onto the system, so we can cancel that out. And it's traveling entirely with kinetic energy to begin with, so there's zero initial potential energy when it comes to the spring. Now, for the second one, it talks about how when it reaches maximum compression. So when it reaches maximum compression, there will be no more kinetic energy because there'll be no more velocity, so that's zero. And because it wasn't mentioned, there is no energy dissipated. Ultimately, you get a pretty simple equation set up to be KEI is equal to PEF, or in this case, PE spring, because the spring is the thing offering the potential energy. So we know that KE is 1/2 mv squared. That's equal to PES, and just plug in known values. That's 1/2 times 0.1 kilograms times 1.2 meters per second squared, and that comes out to be 0.072 joules, and that will be the maximum maximum potential energy after all of the kinetic energy has been transformed into spring potential energy. So that's A, B, and C. Now let's move on to the next part. Question D asks the maximum compression of the spring is 0.1 meters. Calculate the spring constant of the spring. Again, this is another pretty straightforward problem. To this, we must consult our equation sheet. Let's see if we can't get that there. And we want to use this equation right here. US being the potential energy of the spring, 1 equals 1/2 K, the spring constant, times the displacement squared. Now, as it says, it's at its maximum compression. So we can still use the value from earlier of 0.07 joules. And we know that the compression is 0.1 meters. So once more, it's another pretty straightforward problem. Set it up first. PES or US, depends on how you like to write it, is equal to 1/2 K delta X squared. Now with some rearrangement, we can find out that K is equal to 2 times the potential energy over delta X squared. And with known values, again, that's 2 times 0.072 from the previous part, all divided by 0.1 squared. And again, I'll save you the time on the calculations. That comes out to be 14.4. And the final problem gets a little bit more complicated, so let's break it down. Oh, I bumped my camera. So suppose instead that the spring is non-linear and that the force F due to the spring when it is compressed a distance x is modeled as F equals negative bx cubed. Calculate the value of the constant b if the spring is compressed by 0.1 meters. So unlike the previous methods in which we've been using an ideal spring, we can't just use the equations of 1/2 K delta X squared, because this doesn't compress linearly. In fact, as it compresses more and more, the force due to the spring changes by a cubic value. So in order to address this, we have to use some calculus. The C in physics C stands for calculus. If you're not here for calculus, you are in the wrong video. Anyways, so the key fundamental relationship that we were going to want to be using here is that potential energy for a spring is equal to the opposite of the integral of the force with respect to x. What the heck? Hang on. Just real quick, this is totally random. Rob just showed up at my house. Like, uninvited. And like, no one's home. What the heck? Okay.
Oh my god. Alright, come in. Hey, say hi to my physics C optional project video that I'm shooting as we speak. Oh, shoot.
Hi.
Hi.
Oh my god.
Let's go. Give John an A.
Yeah.
And Shree wasn't wearing either thing, and she yelled at us for like 5 minutes.
Hey, play good, I guess. Alright, I gotta get back to finish my video. I was on the last part of the problem I was doing. Come on, Rob.
Tomorrow? Yes.
No.
Yes. Tomorrow's the day of the final. And it's the last day to do.
Have fun at tennis. Anyways, where was I? Alright, one more problem to go.
So, trying to remember. Yes, okay. Using what we know about potential energy and how it relates to force with the spring, you can find out that it's the opposite of the integral of the force with respect to x. And actually, you can see this in the equation sheet we're given. So while the equation sheet gives us the thing for an ideal spring, if you were to integrate this with respect to x to find the opposite of that integral, it comes out to be 1/2 k delta x squared, and it works vice versa with the derivative of the potential energy going to the force. But of course, since this isn't an ideal spring, we can't use the F equals negative k delta x. Instead, we have F is equal to negative bx cubed. So with that in mind, let's solve this problem. The potential energy of the spring then is equal to the negative integral of the F, which we have established to be negative bx cubed dx. Now that's a pretty basic power rule of an integral. Just comes out to be b over 4 x to the 4th. And then we know that this is equal to, once more, 0.072 joules of energy when the potential energy is at its maximum, or when the spring is compressed, 0.1 meters. Because even though it is a non-linear spring and doesn't compress in the same function as the other ones do, the n values are still the same. It'll still reach 0.072 joules at 0.1 meters of compression. So given that, when we plug in 0.1 meters, we can also plug in the 0.072 for the potential energy, and it comes out to be that. And then just rearrange some of the variables. Give me one second. 7.2 is equal to b over 4 times 0.1 to the 4th. B is then equal to 4 times 0.072 over 0.1 to the 4th. That comes out to be, B, no, like, all right, whatever, that's fine. 4 times 0.072 divided by 0.1 to the 4th, 2880. And there you have it. That's this AP Physics C Mechanics FRQ about conservation of momentum as well as conservation of energy, with a little bit of calculus thrown in there for you. All right, there you go. That's all I got. Make it a great day. And Robert, if you're watching this, thank you for interrupting my video. All right, so there you have it. Hang on, say hi to my dog, I guess. Hey boy, come here. Good boy. All right, there you go. Thanks for watching. Make sure you like, comment, and subscribe down below. Hit that bell icon to get notifications whenever we post a new video. And as always, make it a great day.